Have you ever wondered how machines can automatically group similar items without being told how many groups to form? Imagine trying to organize your music playlist by genre without even knowing what the genres are. Sounds tricky, right? That's where hierarchical clustering comes in. It's a smart, unsupervised learning technique that organizes data step by step, forming natural clusters just like a family tree. Hey everyone, welcome back to Knowledge Academy's YouTube channel. In today's video, we're going to master hierarchical clustering, from understanding the concept to actually coding it in Python. Whether you're a data science enthusiast or just curious about how machines make sense of messy data, this video is for you. Ready to dive in? Let's get started. Alright, so what exactly is hierarchical clustering? At its core, it's a method of grouping similar data points based on their features or characteristics. Think of it like organizing your bookshelf. You might first sort books by genre, then by author, and finally by year. Hierarchical clustering works in a similar layered way, creating clusters within clusters. Unlike other methods like k-means, where you have to tell the algorithm how many clusters to make, hierarchical clustering doesn't need that. It builds a hierarchy, a tree of clusters you can visualize using something called a dendrogram. This dendrogram helps you decide how many clusters make sense by cutting the tree at a specific level. Now, to really get a grip on hierarchical clustering, let's break down a few key concepts you'll hear a lot. First is clusters. These are simply groups of similar data points. Second is dendrogram. It is a tree-like diagram showing how clusters were formed or split. Next is similarity. This is measured using distance metrics like Euclidean or Manhattan distance. Now, there are also two main approaches in hierarchical clustering. First, agglomerative, that is bottom-up method. This starts with each data point as its own cluster and merge them step by step. Second is divisive, that is top-down method. This starts with one large cluster and split it into smaller ones. We'll focus on the agglomerative method since it's the most commonly used. Now, let's break down how agglomerative hierarchical clustering actually works, step by step. Start with individual clusters. Every data point is its own cluster. Next, move to measure similarity. Use a distance metric to calculate how close 2 points or clusters are. Then merge the closest clusters, combine the two most similar clusters into one. Then again repeat, keep merging until everything is in one big cluster. Now it's time to visualize with a dendrogram. This helps you see the clustering process and decide how many groups to keep. Now you might be thinking, why should we use hierarchical clustering? Hierarchical clustering is both intuitive and powerful. Let me give you a few reasons to consider it. First, there is no need to guess the number of clusters like in k-means. Second, dendrograms give you a great visual overview of the clustering process. And third, applications range from customer segmentation and genetic analysis to document classification. But of course, it's not perfect. It's computationally expensive for large data sets. Then it's also sensitive to outliers, which can mess up the clustering tree. Now that you've got the theory down, let's get our hands dirty with some Python code. So now we'll build clusters and visualize them using a dendrogram. Ready? Let's go! Before we build any model, we need a problem to solve. Here's ours. Can we teach a machine to identify the species of a flower based on its measurements? Absolutely! So to do this, we'll use the famous iris data set. It's a classic in machine learning and contains measurements of iris flowers, like petal length and width, along with their corresponding species. This makes it a perfect starting point for a classification problem where the goal is to predict a label. In our case, it is the species of the flower. Now, let's load the dataset into Python so we can start working with it. We'll use the pandas library to read the data from an online source. Now for that, we will import pandas, define column names, since the dataset doesn't include headers, and read the CSV file directly from the UCI machine learning repository. This code fetches the dataset and assigns appropriate column names to make it easier to work with. The head function lets us peek at the first few rows to ensure everything looks right. Before building the model, it's important to understand our data. We'll do two things. First, check for missing values or anomalies. Second, visualize the data to spot patterns. Now to check for missing values, we will use is null.sum to check for any missing values in each column and .describe to get a quick statistical summary. This tells us whether we need to clean the data or not. In this case, fortunately, the IRIS dataset is well prepared, so we're good to go. Now let's look at how the features relate to each other. So for that, we will create a scatter plot. This will help us spot clusters or separations that a model might learn from. For this, we will import matplotlib.pyplot. Then we will use .plot and specify the kind of plot we want. After that, we will keep x as petal length and y as petal width and c as species. But here's the catch: since the species are not a numeric column, so here we need to convert the string labels into numeric codes which matplotlib can map to colors. So for that, we will use c equal to data, then in square bracket species. Now to convert it, we will use dot as type on category, then .cat.codes. Here as type tells pandas to treat the species names as categorical values, and .cat.codes assign each species a unique integer. This numerical format is necessary because the C parameter in a scatter plot must receive either numeric values or actual color codes, then in the end C map equal to verdice. Now comes a critical step, splitting the dataset. We don't want to train and test on the same data because that wouldn't tell us how the model performs on unseen data. So, for this we first import sklearn.modelSelection and import train test split. Then we will set features and targets as shown. Here features are independent variable and target is dependent variable. Then next we will separate the features x and y into train and test set. Here we are keeping 80% for training and 20% for testing. This will make our test size equal to 0.2 and random state will be equal to 42. Now that we have done the splitting of dataset for our flower classification task, we need a model that can handle categorical outputs like species names and is easy to understand. That's why we're using a decision tree classifier. It works by asking a series of yes or no questions about the data, like is petal length greater than 2.5 centimeter, then splits the dataset based on those answers. It's perfect for beginners because it's intuitive and lets us see exactly how decisions are made. Now that we've chosen our algorithm, it's time to train it. So for that, we will first import decision tree classifier from sklearn.tree. Then we will initialize our chosen model. After this, we'll use the training data we prepared earlier to help the decision tree learn the relationship between the flower's measurements and its species. We start by creating an instance of the decision tree classifier. Then, using .fitonxtrain and ytrain, we train the model with our training data. Behind the scenes, the model builds a tree structure by learning rules like if petal length is greater than x, its likely species is y. Once trained, it's ready to make predictions. Now that we have trained our model, we'll now test our model by asking it to predict the species of flowers it hasn't seen before, and that is our test dataset. Now, we will use .predict on xtest to generate predictions for the test set. This tells us what species the model thinks each flower belongs to, based solely on the patterns it learned during training. These predictions help us evaluate how well the model generalizes to new data. Once the prediction is done, we'll calculate the model's accuracy to see how well it performed on the test data. So to do that, we will find the accuracy score, where it will compare the predicted species with the actual species in y-test. It returns a score between 0 and 1, which tells us the percentage of correct predictions the model made on the test data. Awesome job! You've just built, trained, and evaluated your very first machine learning model using a decision tree classifier in hierarchical clustering. This is a big step in your machine learning journey. In the next video of this playlist, we're switching gears and diving into single linkage clustering, a cool unsupervised learning technique used for grouping data points. Don't miss it! If this helped you out, make sure to like, share, and subscribe, and tell us in the comments what project would you like to build next.